In 1828, amateur cartographer Edward Quinn finished his magnum opus, the Historical Atlas. Published 2 years after his death, it depicts our knowledge of the world as a flickering light, blowing away clouds of ignorance, unveiling continents and civilizations shrouded beneath. It starts in 2348 BC, beginning with the Bible. The dispersal of the clouds mirror European expansion into the lands beyond. His known world little more than the lands of the Euphrates and Tigris rivers. Time marches on as we step through the pages of the Atlas. Through the exodus of the Israelites and the coming of the Roman Empire, more of the world is revealed. By the early 19th century, the clouds are fully dispersed. All the continents are visible. There is no more land left to discover. Of course, for the artist in China, India, Australia, or the Americas, the focus would be different, each with their own origin story, their own small portion of the world, surrounded by their own darkness. And indeed, these clouds are not solely geographical. All human endeavors begin in a fog of mystery, a fog that only begins to clear when we learn something new. Like the sheathed surface of the Earth, clouds of mystery have also shrouded the universe. Over the last few hundred years, we have turned our attention to the heavens. With our most powerful telescopes, we have peered deeper and deeper into the cosmos. We have spied stars and galaxies, black holes and planets. We have peered back over 13 billion years and seen the very afterglow of creation. We can even deduce the future history of our universe, looking to the days of the last star trillions of years hence, and even further to the time when matter melts and black holes evaporate. One by one, the universe has given up its secrets. The cosmic clouds have steadily been lifted. It might now appear that we have learned all there is to learn about the cosmos. But just as the polymath Simon Newcomb found after claiming we had reached the limits of astronomy in 1888 and dying in 1909 as Einstein was upending the world of physics, it is always a bad idea to bet against further discoveries. And so, this is where scientists find themselves now. Standing tall on towers of complex equations, elaborate theories, and remarkable observational tools, they try to peer further into the fog. But unlike Quinn's Atlas, this is not only a fog of distance. These are clouds that linger around us, within us, before us. These are new universes born beyond our cosmic horizon, in our distant cosmic past, even inside us with every instance that passes. As our knowledge of theoretical physics has grown, what had once seemed radical has gradually forced its way into possibility and even probability. Multiverse theories have proliferated, hoping to answer the deepest questions about what we and the entire cosmos is. From parallel worlds of infinite hues to barren deserts of endless nothing, scientists are blowing away the cosmic fog of unknowing, revealing a warped Russian doll of infinities, nestled both within and right next to each other. Welcome to the Multiverses. According to the European Space Agency, there are approximately 100 sextillion stars in the observable universe, and across the cosmos they form huge filaments and clusters. But on a more personal level, have you ever wondered what the night sky looked like when you were born? Under Lucky Stars have been kind enough to support this video, and their beautiful framed star maps are a great gift option to remember an important moment in your life. A personalized chart with over 15 designs to choose from and printed on durable museum-quality paper, showing what the stars were like on a day and time you choose. They are the original star map maker, and their methods are verified by NASA astrophysicists and enjoyed by Neil himself. They also sent me one over, and Coco absolutely loves it. Really ties the room together. The company are also committed to keeping the skies clean, organising fundraisers for the International Dark Sky Association. It's a great, thoughtful gift for someone, or indeed yourself, especially as they're now offering an exclusive 10% discount to History of the Universe viewers. Head over to underluckystars.com/universe and use your code UNIVERSE to start your star map journey. In April 1920, a great debate was held at the Smithsonian Museum of Natural History in Washington, D.C. On the stage were Harlow Shapley and Heber Curtis. Both renowned astronomers, Shapley was well known for mapping the locations of stars throughout the Milky Way. Curtis, the first to observe a thin stream of material in the object M87. Though he didn't know it at the time, he had discovered a relativistic jet of matter ejected from an immense black hole. The topic of their debate: just how big is the universe? The two camps presented their arguments. Shapley argued that the cosmos was small. The stars of the Milky Way, he claimed, were the entire universe. That was it. There was nothing beyond. He knew that astronomers had spied several strange nebulae through their telescopes, but these, he told the audience, were features buried within the stars of the Milky Way. Curtis, however, objected. He was no fan of this compact cosmos. Instead, he argued the universe was large, much larger than most astronomers were comfortable with. The spiral nebulae, he declared, were not within the Milky Way, but were many millions of light years away. Each was an island universe, an individual galaxy home to billions of stars. And there could be uncountable galaxies beyond the edge of the Milky Way. Eventually, the debate came to a close. The audience had been taken on a wild ride across the universe, but there was no clear winner. Shapley and Curtis went their separate ways, and the size of the universe remained unsolved. But things were changing quickly. On the other side of the country, Edwin Hubble had recently joined the Mount Wilson Observatory in California. He was on a quest to answer the question of the size of the universe once and for all. The timing was fortuitous as the world's largest telescope, the 100-inch Hooker, had just been installed. It was the ideal instrument for surveying the sky and charting the distances to heavenly bodies, and Hubble's first target was the fuzzy nebula in the constellation of Andromeda. He knew that astronomers had seen individual stars within Andromeda's nebula, but just how far away were they? They could be intrinsically faint stars that were closer, or they could be extremely luminous stars spied at a very large distance. Astronomical evidence had been building for several years. In fact, in 1917, it was Heber Curtis who had discovered an exploding star, a nova, within Andromeda's nebula, and in search of older photographic plates, he spotted 11 more, much fainter than any others that had been observed. But Hubble was searching for something different. He was scouring Andromeda for stars whose brightness varied. Lots of stars can change their brightness, but Hubble was after a particular kind of variable star, a Cepheid variable. These were stars whose brightness varies with a regular beating pattern. In 1912, Henrietta Swan Leavitt had realized that how long the beat of a star takes depends on how luminous the star is. Fainter stars beat rapidly, brighter stars beat more slowly. This meant that if you observe a Cepheid variable star and measure how long it takes to beat, you can deduce how luminous it truly is. And once you know its luminosity, you can work out how far it is from how bright it appears in your telescope. It was these standard candles that Hubble was searching for, and he found them, buried within the fuzzy light of Andromeda. Once he measured the regular beating of these stars, the picture became crystal clear. Hubble was observing bright, giant stars many hundreds of thousands of light years away, far outside the Milky Way. In 1924, Hubble sent a letter to Shapley telling him that Andromeda is a galaxy in its own right, and that the other nebula spied through telescopes must also be galaxies, at immense distances. The great debate was settled. Curtis was correct. And Shapley's response? Here is the letter that destroyed my universe. The clouds parted, and our cosmos suddenly became much, much bigger. And throughout the 20th century, we have continued to peer deeper and deeper into our universe. In measuring distances, millions of light years became billions of light years. But was there a limit to how far we could see? In 1964, a chance discovery of a hiss of radio emission from all over the sky marked the limit of our observations. The cosmic microwave background radiation, whose light has been traveling for 13.7 billion years, marked the edge of the map, a boundary between the observable universe we can see and what we cannot. This, of course, leads us to ask, just what is beyond the observable universe? Through the 20th century, telescopes got bigger and astronomers saw further, but with their paper and pens, the theorists were also hard at work. Building on the insights of Einstein and Friedman, astronomers now had a mathematical description of the cosmos. Belgian cleric Georges Lemaitre realized that the universe was not infinitely old, but had been born at a finite time in the past. He called this initial event the cosmic egg, the ultimate origin of the cosmos. And from this fiery birth and expansion in the Big Bang, the universe had been cooling and changing for billions of years. But what did their equations say about the size of the universe? They realized that the universe we see around us, the observable universe, must only be part of a much larger whole. Given the finite age of the universe, we can only see the bits from the universe from which we have received light. And beyond this observable space, there must be more. More universe, more galaxies, more stars, more planets. But how much can there be beyond the horizon? And it is here that we meet the first of our infinities. The cosmological equations suggested that there might be an infinite amount of space in all directions. As the universe most likely had no spatial curvature, then it had to go on forever. This might seem strange given that the universe was born a finite time in the past, expanding from a single point. But if the cosmic equations are correct, and the universe is infinite today, it always has been, even at its birth. From an infinitely dense cosmic egg, it has simply gotten less and less dense. And all we can observe is the small patch around us, our observable universe, embedded in the infinite. But as the cosmos ages, more and more of it should come into view as the observable universe grows. Eventually, we should be touched by the light of countless distant stars. And if we wait long enough, maybe an infinite amount of time, eventually we will see it all. Or so we thought. But by the end of the 20th century, everything had changed. And this change shook our understanding of the universe to its very core. At the close of the 1990s, astronomers announced the unexpected discovery of the accelerating expansion of the universe. The culprit was dark energy, a mysterious, repulsive something that filled the cosmos. It was realized that galaxies were and are moving away from each other faster and faster. But what did this mean for our observable universe? As time marches on, our map will once again be plunged into darkness. We will begin to lose sight of galaxies outside our own. In about 100 billion years from now, all other galaxies will have vanished completely from view. Beyond our local stars, there will be nothing but the blackest black. At every moment, there is less and less of the universe we will ever be able to explore. Astronomers estimate that there are about 2 trillion galaxies within our observable universe, and that due to the accelerated expansion, almost 99% of those galaxies are already beyond our cosmic horizon. If we could set off in a spaceship skimming close to the speed of light, we would never arrive. But though we will never visit these distant worlds or feel the warmth of their suns, we can use logic to deduce their properties. Let's start with the simplest picture of all, that beyond is an infinity of space in all directions, and that the universe over the horizon is just more of the universe we have here. Not exactly the same, just the same in character, born 14 billion years ago and containing more stars and galaxies. If we pick one of these galaxies at random, it will sit at the center of its own observable universe, surrounded by trillions of other galaxies. It will be at the center of its own bubble of observability in the infinity of the universe. Just as a Native American would have produced a different historical atlas to the Englishman Edward Quinn, so would their outlook be their own, but with a key difference. The inhabitants of this universe always have been, and always will be, completely separate from us. Being causally disconnected means that no light rays, no signals of any kind can be exchanged between the regions. They are beyond each other's horizons and are destined to be forever so. Universe upon universe out there in the void. And it is now things begin to get complicated. So let's start with new definitions. Let's call something like our observable universe simply a universe. So, beyond our horizons, there are countless other universes. But what do we call the universe that contains this myriad of individual universes? Welcome to the first level of the multiverse. It is important to note that this is just a multiverse, one of many ideas that carry that name. The physicist Max Tegmark calling this a level 1 multiverse. Let's explore. As we know, in this particular multiverse beyond our horizon, there is possibly an infinite number of other universes, rich in stars and galaxies just like our own, with the potential for life, just like our own. However, if we follow this logic and think a little harder, a disturbing picture emerges. In our level 1 multiverse, each individual universe is roughly the same size. Each contains similar numbers of atoms arranged as planets, stars, and galaxies. But with an infinity of space to play with, strange things can occur. Out there in the void, some of these universes will be identical to ours, absolutely and precisely the same. In this other universe, there will be a Milky Way galaxy containing a star identical to the Sun. And orbiting this star will be a planet identical to the Earth with continents, oceans, plants, and animals. And of course, there are people. Everyone you know and don't know are there, playing out their copies of their lives. And finally, there will be another version of you, watching this exact video. Such a situation would be vanishingly rare, with most universes being only roughly similar to our own, but a vanishingly rare percentage of infinity is still infinity. How far away is this doppelganger? Max Tegmark estimates something like 10 to the power of 118 meters. This is much, much larger than the roughly 10 to the 27 meter diameter of our universe. And of course they are causally disconnected, so you will never interact with them. But they would be out there in the infinite, along with every possible variation. Anything that has a chance of happening must happen somewhere in the infinite, somewhere in the level 1 multiverse. Of course, we are forever locked within our own observational universe, forever bound to see nothing but our tiny patch, the infinite parallel worlds of the level 1 multiverse lost behind our cosmic horizon. And yet, this is just the beginning. This is just level 1. Just one mind-melting deduction from our laws of physics. There are 3 more levels in Max Tegmark's multiverse of multiverses, and with each step, our picture of the cosmos becomes even stranger. Why does our universe have its particular laws of physics? This might seem like a strange question. How could it have been otherwise? But as our knowledge of the workings of space advanced across the 20th century, it became harder and harder to ignore. In the 1960s, cosmologist Robert Dicke suggested that the forces of gravity and electromagnetism were finely balanced. If they were not, stars simply would not shine and life in the universe would be impossible. And as physicists stared deeply into their equations, more examples of this fine-tuning were revealed. Astronomer Fred Hoyle found that tiny changes in the nuclear forces would result in a universe without carbon, and Steven Weinberg noted that a universe with more dark energy would expand too rapidly for stars to form. Serendipity piled on top of serendipity, and it became apparent that if our universe were even very slightly different, we simply would not exist. Our cosmos appeared to have been just the right physics to allow for the complexity of life. And it is in that key adjective that the answer lies. Our cosmos. It is through this problem we can take our first steps into the Level 2 multiverse. Although there is more than one way to build a Level 2 multiverse, we will start with the idea of inflation, a burst of rapid universal expansion in its earliest moments. When originally proposed by Alan Guth, inflation turned on and off in a trillionth of a trillionth of a trillionth of a second, smoothing the universe and seeding the structure that led to the formation of galaxies. It seemed an essential ingredient for explaining the universe around us. But there was immediately a problem that threatened the very idea. How could inflation be synchronized across the entire cosmos within this tiny window of time? Calculations suggested that the end of inflation would be incredibly messy. Whilst in some places inflation would come to an end after a short burst, in others inflation could continue. This lack of a graceful exit appeared to spell doom for the theory. But inflation was too attractive to simply abandon, and by the 1980s a flurry of activity gave birth to the new theory of inflation. Its key architects were André Linde, Andreas Albrecht and Paul Steinhardt. And it was this second wave of thought that introduced a now essential part of the idea, the inflaton. The inflaton field permeated the early universe and provided the impetus for inflation. This new inflation embraced the messiness of the original inflation. As the cosmos inflates, instead of ending everywhere, individual universes continually crystallize out of the inflation. In this picture, inflation never ceases. It continues for eternity. And as it does, more and more universes crystallize. Within this eternal inflation, our Level 1 infinite multiverse is just one of countless many, separated by ever-inflating space and time. So here we sit at the center of our observable universe. Across the horizon, there is more universe that we can never explore. And beyond that, inflation continues, carrying away the other infinite Level 1 multiverses that we will never know. Of course, many questions remain, none less than just how a universe would emerge from the eternal inflation. Some have suggested the process is similar to the formation of bubbles when opening a soda. And it is this bubble nucleation that cements the properties of the universe it forms. Not just the overall properties, but the intricate details. This includes the very laws of physics themselves, meaning that in some universes the forces of nature would be different. In others, the masses of the fundamental particles would be different. And in others again, there might be more or fewer dimensions of space and time. Physicists have wondered what these other multiverses would be like, and they have arrived at a stark conclusion. Virtually all of these other Level 1 multiverses would be dead and sterile, lacking the complexity essential for life. Though within this endless sea of dead universes there would be tiny pockets of habitability, and it is no surprise that this is where we find our universe. In this Level 2 multiverse, our Level 1 multiverse is one of the lucky few that can host complexity and life. The apparent fine-tuning of our physical laws, little more than a statistical fluke. A roll of an infinite dice across an even higher infinity. But this is not the only Level 2 multiverse that has been proposed. There are other theories that would require a multiverse of which our Level 1 existence would only be a part. And in fact, Paul Steinhardt, who developed the new theory of inflation in the 1980s, plays a key role in a completely different idea. In Hindu cosmology, the universe is without beginning or end. Instead, it is cyclical, with each cycle lasting for 4,320,000 years. Each universe starts with rebirth and perfection, a time of enlightenment. As it ages, the universe degenerates and decays before ultimate destruction and eventual rebirth. But what of the physical universe? Could it, too, be truly cyclical? Since the dawn of modern cosmology, many minds have pondered this question. In the 1920s, physicists, including Einstein, explored this very possibility. Within the cosmological equations derived from general relativity, the prospect for a cycling universe existed. Indeed, the idea that our universe was just one of an infinitely repeating cycle was far more comforting than a universe born from nothing. But there was a lingering problem, and that problem was entropy. Entropy is a measure of disorder, the inexorable running down of the cosmos. At every moment, through every process, useful energy is being degraded into useless energy. Life on Earth is completely governed by such processing of energy. From a fire turning wood to ash, to the running of a cheetah turning food into movement, energy is used. And whilst the total flow of energy balances, energy in equals energy out, the entropy, the movement from potential to disorder, continues to increase. Across the universe, this is unavoidable. At the end of time, the disorder will be greater than at the start. There is no way to escape. And so, if a universe is just part of an endless cycle, this entropy is passed from parent to child, every cosmos beginning encumbered with the disorder from all the universes that existed before. And if there is an endless, maybe infinite cycle of universes, how can there be order at all in our current universe? And it was this inexorable increase of entropy that doomed the concept of a cyclical universe to the wastebin of forgotten ideas. Although, sometimes, it is hard to completely kill a scientific theory, and the concept of a cyclical universe has itself been recycled. Recent Nobel Prize winner Roger Penrose proposed the conformal cyclic cosmology. He suggested that in the extreme distant future of our universe, all matter must decay away into nothing, and that the resulting empty universe will continue expanding into eternity. When it is large enough and empty enough, it will be a very simple, featureless place, featureless like our own universe at the start of the Big Bang. Penrose then hypothesized that the past and the future are effectively one, a constant cycle between cosmic birth and cosmic death. And that is just one example. In the 1980s, physicist Lee Smolin suggested that a baby cosmos could be created when black holes formed, tearing space and time, this tear giving birth to an entire new universe. Not a birth in the existing cosmos, but spawning a completely new universe of space and time. If this idea has even the spark of truth, then every single second a new cosmos is born from a stellar death in our universe. Smolin, however, went further. Borrowing from Darwinian evolution, he wondered if the baby universe could mutate and be different to its parent. The differences lying in the laws of physics underlying the cosmos. If the mutation is too severe, gravity may be too weak, or there may be not enough atoms to form stars. Such a baby universe is an evolutionary dead end, but those that can form stars and form black holes beget more baby universes. Eventually, these star-forming universes must come to dominate in the evolutionary tree of the multiverse. As stars are essential for the habitability of our universe, Smolin's multiverse could be teeming with life. Of course, there is a lot of uncertainty in Smolin's cosmic natural selection, and whilst it is intriguing to think about, not everyone is convinced. Finally, the cyclic universe was recently reborn again, but this time in fire. Think of the phoenix, the immortal bird of Greek mythology. It lives its life in cycles, dying in old age in a burst of flames. But from the ashes, the phoenix is reborn to live its life again. And this is where Paul Steinhardt reappears. In conjunction with Neil Turok, he has since come to reject his own inflationary theory and proposed a new Level 2 multiverse, the ekpyrotic universe. Developing out of string theory, for them our entire universe floats in higher dimensions, like a sheet blowing in the wind. Here, cosmic rebirth occurs when multiple cosmic sheets collide. Huge amounts of energy are released, forming the matter in the cosmos. And the newborn universe has low entropy, the Phoenix universe rising from the ashes. But today, it has few true supporters. Many physicists have trouble accepting the notion of sheet universes floating in higher dimensions. However, recently this concept has gained widespread attention, and the answer may lie in one of the most complex and mind-blowing theories of all. Ed Witten followed a rather unconventional path on his way to becoming a professor of physics. In 1971, he completed an arts degree in history and linguistics. He tried journalism and politics, eventually enrolling in and dropping out of a graduate program in economics. By 1976, he had finally found his niche, completing a PhD in fundamental physics and exploring how the universe works. Witten's mathematical insights about the topology of space and time set him apart from other physicists. In 1990, he was awarded the Fields Medal for his work. Often called the Nobel Prize of Mathematics, it is usually awarded to mathematicians. But by this time, Witten had set his sights on bigger things. Indeed, one of the biggest dreams in physics. A single theory that encompassed everything we knew about the universe. The theory of everything. But he was just the latest in a long line who had hunted and failed to find this physics El Dorado. Just why was this search so hard? Of the 4 fundamental forces of nature, 3 are written in the language of quantum mechanics. These are the strong and weak nuclear forces and electromagnetism. Our best description of gravity, however, is Einstein's general theory of relativity, a distinctly non-quantum theory. Gravity is described by the curving and bending of space and time. Why the forces of nature are written in 2 different mathematical languages has long bothered physicists. There is a feeling, at least a desire, that the true mathematics of the universe should be one. One neat single theory encompassing all the physics of the universe. And so, physicists have searched for this theory for a very, very long time. Early attempts to unite gravity and electromagnetism were made by Theodore Kaluza and Oscar Klein. They added more dimensions to Einstein's relativity, but ultimately failed in their quest. Other great names also litter the path of failed theories of everything. This includes Einstein himself, as well as Hermann Weyl, Arthur Eddington, and David Hilbert. By the 1970s, a brave new contender, supergravity, had been proposed. This was based upon a mathematical formalism to iron out problems in our understanding of fundamental particles. Known as supersymmetry, it suggested that particles should have strange alter egos. For electrons, there should be selectrons. For quarks, there should be squarks. And most counterintuitively, the mathematics of supergravity seemed to work best in 11 dimensions. But as scientists peered more deeply into these equations, things began to unravel. The universe predicted by the ideas of supergravity just didn't match the one we inhabit, and eventually, supergravity quietly fell by the scientific wayside. But, again, it can be difficult for scientific theories to completely die and disappear, especially those with the prefix super. And so, in 1984, superstring theory was born in the minds of Michael Green and John Schwartz. The key idea of superstrings is that all fundamental particles are really the same thing. Each is really just a vibration on a loop of stringy stuff. Different notes on the strings correspond to different particles. One note for an electron, another for a quark. And just like supergravity, superstrings need far more dimensions than we experience day to day. In its earliest mathematical form, superstring theory was written in 26 dimensions, though eventually things settled down to a more manageable 11, echoing its super ancestor. A way was found to hide the extra dimensions, a process known as compactification. Unlike our everyday dimensions of up, down, and across, these supposed extra dimensions were curled up on a microscopic scale, potentially as bizarre geometrical shapes called Calabi-Yau manifolds. And just as we cannot experience the individual atoms in the air, we cannot experience the existence of these microscopic dimensions. Again, physicists were excited. Again, they thought they were about to arrive at a theory of everything, a complete description of the universe. And again, their hopes were dashed. They had hoped that a single mathematical framework for the theory of everything would emerge. But the mathematical complexity grew and ideas splintered. In total, there were 5 different versions of string theory following 5 different paths towards enlightenment. By the mid-1990s, frustrations had reached boiling point. And that was when, in 1995, at the annual String Theory Conference in the University of California, Ed Witten put a new idea on the table. Perhaps these 5 differing theories weren't so distinct, after all. Perhaps they were all the same theory, intrinsically linked. It was from this revelation M-theory was born, and the second superstring revolution was begun. No one seems to remember what the M in M-theory stands for. Some say mystery or perhaps magic. But to many, it stands for membrane, reflecting how the one-dimensional strings of string theory are drawn out into sheets or branes within the higher dimensions. This eases some of the mathematical issues facing string theory, but it does not solve them. And in truth, M-theory isn't yet a theory. It is more of an idea, a dream, a goal to which physicists are working. But it has brought one thing, however, into sharp relief. The original hope was that the theory of everything would be pure and unique. It would explain why the electron has the mass it does and why gravity has the strength it currently does. That hope died with M-theory. M-theory predicts that due to the intense heat in the first moment, the early universe would be featureless and simple. As the universe cools, the fundamental features of physics crystallize out. But this crystallization of the laws of physics would not be unique. There would be uncountable ways that this crystallization could occur, each resulting in different fundamental physics, different particle masses, and different forces. Physicists refer to this myriad of possible combinations of the laws of physics as the string theory landscape. How many solutions are there out in the landscape? Nobody really knows. It might be 10 to the power of 500, or it might be infinite. Once again, our supposedly fine-tuned universe finds another dice to roll. And indeed, some physicists have gone much further and suggested that these possible universes are not just possible. They really do exist. In this picture, the multi-dimensions of M theory, an entire universe can exist on a membrane or a brane. And in this space of multi-dimensions known as the bulk, there are an uncountable number of branes. For each universe floating in the bulk, the crystallizing features of physics will be different. Differing universes will find themselves at differing locations in the string theory landscape. There are clear parallels to the bubble multiverses of eternal inflation. As we've already seen, a random mix of physical laws is most likely to end up with a universe that is simply dead and sterile. And as the vast multiverse of eternal inflation brings about a desolate graveyard, so too would the M-theory bulk be a grim sight. But every so often, somewhere in the mix, there would be a universe that won the multiverse lottery. And unsurprisingly, we find ourselves in such a lucky universe. Of course, given the undeveloped form of M-theory, much of this is pure speculation. We don't know if the string theory landscape is real, or if universes do exist as branes in the bulk. But to some physicists, M-theory simply feels right, and a brane multiverse feels inevitable. Only time and intense mathematical effort will tell. And so, the fog of unknowing has retreated and revealed a plethora of possible level 2 multiverses, some contrasting, some able to work in harmony, some currently in scientific favor, and some out. Our finite observable universe sits within its larger, infinite multiverse, perhaps crystallizing from eternally inflating bubbles, or reborn in fire from a previous multiverse, or resting on a vast brane floating in the bulk of hyperspace. The clouds are parting. Is this the end? Is this as weird as it gets? In a word, no. What if I told you that you are immortal? That you will live forever? What if I could guarantee that no matter what challenges confronted you, you would emerge victorious? What if I told you that you will, with all certainty, conquer illness and even death? With a gun pointed at your head, I could ensure your survival. You might think that I am mad. But we have now arrived at the level 3 multiverse, and here, immortality is guaranteed. We begin with a seemingly simple insight with earth-shattering consequences. The question of the fundamental nature of light. By the year 1800, whether light was a wave or a collection of particles had been argued over for more than a century. But a new experiment was about to seemingly provide a definitive answer to this question. The experimenter was Thomas Young, a polymath known by some as the last man to know everything. Over his life, Young made important contributions to medicine, music, and language. Indeed, he was instrumental in deciphering Egyptian hieroglyphics and the Rosetta Stone. But we are interested here in Young's many contributions to physics. And so it was in 1801 that he turned his impressive intellect to the nature of light. His experimental setup was deceptively simple. It consisted of a source of light and a screen. In between the source and screen, Young placed another screen containing 2 narrow slits. He reasoned that if light was composed of particles, some would fly through one slit and some would fly through the other. This would result in 2 bright spots of light on the distant screen. However, if light was a wave, this wave would pass through both slits, radiating outwards towards the screen. Instead of just 2 spots of light, the result would be a complex mix of brightness and darkness, an interference pattern. Young set up his experiment, shrouding it to ensure complete darkness. He directed sunlight through a small hole to act as a source, and then he inspected the screen. And it was there he found the beautiful pattern of interference. Indisputable evidence that light was a wave. This viewpoint lasted a century. But as it has since tended to do in the world of physics whenever it has raised its head, quantum mechanics came along and seriously muddied the water. The key message of quantum mechanics was that the superficially continuous universe of classical physics was actually quantized, chopped into discrete chunks, and this included light. It was Einstein who first proposed the discrete nature of light, tiny particles we now know as photons. But this left scientists with a simple but fundamental problem. If quantum mechanics says that light is truly particles, how could they explain Young's observation of an interference pattern? This strange duality, light as both a particle and a wave, has been argued about for more than a century, and to understand it and its far-reaching implications, we need to explore the language of quantum mechanics. To Galileo and Newton, objects could be described definitively. That was there, this was here, and things move at the speed that is measured. In classical terms, an electron has a definite position and a definite velocity. In the mathematics of quantum mechanics, however, the definitive language has to be abandoned. In quantum terms, an electron is now defined by a wave function. This wave function encodes all the properties of the electron, but it has no unique position or unique velocity. It is smeared over space. In 1926, Erwin Schrödinger derived an equation that allows us to determine how a wave function changes with time. And it is with this equation we can calculate how light or any quantum particle flows through Young's slits. As the wave function is a wave, and waves can interfere, we get interference at the screen. Problem solved. But not quite. Let's run Young's experiment again. In 1801, he used photographic film to detect his light waves. But today we use electronic detectors, and with the newfound accuracy they provide, it is clear that single particles are detected on the screen. Single particles that are not smeared out like their wave function. The light travels as a wave, thus creating the interference pattern. But the photons actually interact with the screen as particles, single points. This is true for all quantum particles, and this is where the real problems begin. How does this smeared out wave function turn into a discrete electron or photon? It was two of the giants of quantum mechanics, Niels Bohr and Werner Heisenberg, who first put a solution on the table. Named the Copenhagen interpretation of quantum mechanics, at the time it was a radical development, for Bohr and Heisenberg put the observer squarely in the experiment. It is the observer that demanded an outcome. To understand this, the wave function has to be interpreted as a wave of probability. This idea was first proposed by Max Born in 1926. He said that you should expect to find your photon or electron where the probability amplitude is high, and to be rarer in places where your probability amplitude is low. But an extra ingredient is needed to turn your wave function into the detection of an individual photon or electron. You need the wave function to collapse. So when you fire an individual particle through Young's slits, its wave function fans out. The wave function goes through both slits, fanning out again and interfering on its journey towards the screen. But at the screen, the wave function collapses to a single detection. We cannot predict exactly where on the screen the particle will be detected, but its location will be dictated by the probabilistic amplitude of the wave function. Many experiments over the last century with photons, electrons, and other particles have borne this out. But there is a problem with the Copenhagen interpretation, and it is this problem that will eventually lead us to our only Level 3 multiverse. Nowhere in the successful mathematics is the mechanism for the wave function to collapse. The wave function collapse has to be bolted on, an ad hoc piece of mathematical machinery that seems to have no real justification. This is one of the most furiously disputed questions in physics, what quantum physicists call the measurement problem. Some have claimed it is the act of detection that collapses the wave function, with John van Neumann even suggesting that consciousness is needed for collapse, the presence of the observer becoming critical to the outcome of the experiment. Indeed, this leads to some bizarre questions. Does that mean no wave functions collapsed until the first consciousness in whatever primeval creature arose? It does, however, remain a popular interpretation often taught to students who are new to quantum mechanics. But to many physicists and philosophers, collapsing wave functions are more than discomforting. Cosmologist Sean Carroll went as far as to say the need for the wave function collapse should be very embarrassing to physicists. And so, other interpretations of quantum physics have been proposed, and the most controversial of these is something known as many worlds. In 1942, a 12-year-old Hugh Everett III sent a letter to Albert Einstein, asking whether the universe was held together by chance or unified by some kind of force. Dear Hugh, there is no such thing as an irresistible force and immovable body. But there seems to be a very stubborn boy who has forced his way victoriously through strange difficulties created by himself for this purpose. Sincerely yours, A. Einstein. And it was 12 years later, in 1954, that this stubborn boy came up with what would be his singular contribution to theoretical physics during a late-night drinking session, ruminating on the ridiculous things about the nature of quantum mechanics. His aim was to follow the mathematics of the theory, real-world consequences be damned. He wanted to tackle the measurement problem head-on. The Copenhagen interpretation is hopelessly incomplete because of its prior reliance on classical physics, as well as a philosophic monstrosity with a reality concept for the macroscopic world and denial of the same for the microcosm. Indeed, as we've seen, the Copenhagen interpretation relied on this so-called Heisenberg cut, the ad hoc line between the micro and macro which held the more bizarre features of the quantum world at bay. Everett rejected this. He threw the notion of wave function collapse out the window. Let's begin by thinking about an experiment in a laboratory. Once set up, traditionally the experimenter is distinct from their apparatus. They can influence the experiment by adjusting the temperature or magnetic field, but they are just an observer, not part of what is being experimented on. Everett realized, however, that this cannot be correct. The experiment is made of electrons and nuclei, each described by individual wave functions. In terms of quantum mechanics, this experiment is a superposition of all its wave functions. And so is the experimenter. To fully describe the laboratory, we need to consider the superposition of experiment and experimenter. The entire laboratory is a superposition of all the particles within. But if the experimenter is now coupled to the experiment through superposition, where is the collapse? The problems only get worse from here. Everett realized that the experimental laboratory is not isolated, but is part of the universe. The total wave function, the universal wave function, should encode the properties of every particle in the universe. Within this universal wave function is all of the particles that make up you, and as in all of quantum mechanics, the Schrödinger equation churns the universal wave function into the future. But if this is the case, where has the probabilistic aspect of quantum mechanics gone? Everett proposed that the universal wave function encodes more than just our universe. It also encodes all of the possible universes as a superposition of universal wave functions. Within these universes, an electron would be in a supposition of two states, but the act of observing the electron severs this supposition. the coherence between nearby universes is broken by the observation, and all the universes decohere. In some universes, the electron is found to be definitively in state A. In others, it is definitively in state B. And remember, you are in the universal wave function, so you in some universes measure the electron in A, and you in other universes measure the electron in B. Effectively, two separate universes have become distinct within the universal wave function. And this would happen at every quantum measurement, at every quantum interaction. Every probabilistic outcome in quantum mechanics is played out within the superposition of universal wave functions. Individual universes with distinct futures crystallize out of the ultimate superposition. In many worlds theory, the other universes are just as real as our own, and in some of them there are other versions of you. In nearby universes which hold coherence, these other versions of you are almost identical to the one you are experiencing. But in another universe, somewhat more distant in the mix and distinctly separated from our own, you are very different. In others, you don't exist at all. This feels very much like the level 1 multiverse we encountered earlier, with parallel worlds playing out. But in reality, in the level 3 multiverse, every branching universe can be its own level 1 multiverse, or even level 2. Infinities upon infinities, and more worlds beyond worlds. From Young's seemingly simple double-slit experiment, we have arrived at what Max Tegmark calls the level 3 multiverse. In removing the need for collapse of the wave function, we have ended up with an endless sea of parallel universes. Some physicists dismiss many worlds out of hand, calling it exceedingly wasteful. Nobel Prize winner Geraint Lewis went as far as to say it would be a stupendous number of parallel worlds, which are only there because physicists couldn't decide which of them is real. And indeed, Everett's insights were largely ignored during his lifetime. After receiving the cold shoulder from much of the physics community and Niels Bohr himself, he left physics after completing his PhD, going on to work as a computer programmer and dying of a heart attack at the age of just 51. But his ideas resonated with a new generation of physicists, with a resurgence of interest in recent years. To some, many worlds represents the only realistic solution to the various interpretations of quantum mechanics, the only way to truly follow the science and explain wave function collapse. But there are still questions. Not least of all, consciousness. What happens to the you that makes you as individual universes diverge? Are there two distinct versions of you, each now imprinted with the memories and experiences before the split? It is in such exciting playgrounds that philosophers love to play. Imagine you have a coin, a perfectly fair coin with equal chances of coming up heads or tails. The stakes on flipping this coin are high. Tails, you are executed. Heads, you survive. As the coin spins in the air, you know that the outcome is 50-50. The coin lands and settles on heads. You sigh with relief. But you are instructed to toss the coin again, and again, and again. You realize this is a game you are bound to lose. You would have to be extremely lucky to keep getting heads on every throw, and so your execution awaits. This is what you ultimately face with the Copenhagen interpretation of quantum mechanics. With many worlds, however, on the first toss, the universe splits in two. In one universe, the coin came up heads and you survived. In the other universe, the coin came up tails and you died. And on the second toss, the universe split again, into one universe in which you live, another in which you're executed. The lucky path of a continuous run of heads will exist through the superposition of possible universes. One future history will guarantee eternal survival. What would the coin tosser experience? Will they find themselves on the lucky, immortal path? Given the mysteries of consciousness, nobody knows. It may seem that we have come to the end of our exploration of multiverse ideas. What possibly could contain more than the ultimate universal superposition of all possible universes? To get to this point, we have already rid ourselves of the usual understanding of reality. We've had to consider parallel worlds beyond our own, vast, nested infinities stretching out beyond eternity. But to arrive at the next step, we will have to completely and utterly let go. For in the level 4 multiverse, we may be little more than a mathematical dream. What is reality? As you look around, it seems obvious. You are surrounded by stuff, some solid, some liquid, and some as ethereal as the air. But you should know by now that this reality is an illusion. If you peer closely enough, it is all made of atoms combined into various molecules, and we can strip back reality even further. Atoms can be dismantled into smaller pieces, particles such as electrons and quarks. Do these fundamental particles represent the purest representation of reality? Not quite, as we also need to include the ways these particles interact through the fundamental forces. Of course, all this is written in the language of mathematics, numbers and equations that describe reality. But where do the rules of reality exist? This might seem like a very strange question. Where could these rules, written in the language of mathematics, exist? And it is now that we arrive at Max Tegmark's Level 4 multiverse. This multiverse is filled with nothing but mathematical structures encompassing the entire realm of possibility. These mathematical structures can encode every kind of universe. Within this Level 4 multiverse, every other multiverse can be found. It is the ultimate ensemble of every kind of reality, and much, much more. Indeed, this theory bears a lot of similarities to the simulation hypothesis, that our reality is nothing more than a super powerful program on a computer in a universe above ours, its programs written by beings to whom we are but playthings. But the Level 4 multiverse Max Tegmark proposes would be more than just a physical computer. It would be an existence of just math. And so, we now rest at the edge of speculation after speculation, theoretical reach after theoretical reach. The ultimate view of the multiverse. We started our journey by peering over the horizon and wondering what was beyond. We now find ourselves gazing at the meaning of reality and questioning our very existence. What is clear is that the multiverse is not a single concept. It is more a grab bag of ideas, some built on solid science, some almost science fiction. And so before we end our exploration, a word of caution. Discussions of the multiverse in the public arena often end in shouting matches. For some physicists, the multiverse seems inevitable. Ideas like eternal inflation are simply too alluring to be wrong. Other physicists are certain they are on the right path with M-theory and the existence of the string theory landscape. Even the seemingly simple idea of wondering about dark energy and our cosmic horizon implies some kind of multiverse. But some still vehemently oppose the notion. To them, talking about multiverses that are forever beyond our grasp is unscientific. Ideas, they tell us, are only scientific if they are amenable to scientific scrutiny, and therefore parallel universes that will never be visible to telescopes or microscopes should be struck from science. But in truth, neither side holds the scientific high ground. In reality, our multiverse ideas are simply too early in development to truly question their scientific validity. Some of the foundational mathematics might be in place, but so many mysteries still abound. Questions like how universes crystallized out of eternal inflation remain unanswered. String theory is hugely popular, yet has no definitive proof behind it. The many worlds of quantum mechanics has some passionate backers, but remains just an interpretation. And Tegmark's mathematical structures of the Level 4 multiverse a little more than a dream. But none of this means that the multiverse will be forever off limits. With enough mathematical effort, we might find a crack into parallel worlds. We might find complex space-time structures akin to the idea of wormholes that will bring the seemingly unseeable into sight. Some have suggested that patterns may be written into the sky in the cosmic microwave background. These, they claim, might be the scars of universal collisions in the many dimensions of M-theory. The cosmic microwave background could also give us suggestions as to whether our universe is flat and therefore infinite, or simply too large for us to see the curvature. The search continues. But for now, contact or evidence of these alternate worlds is little more than wishful thinking. We have no idea how theories will be developed into the future, and we simply have no idea if the multiverse will ever be spied through our telescopes or experimented on in our laboratories. In reality, the multiverse may be forever hidden within the fog. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave a comment to tell us what you think. Thanks for watching, and we'll see you next time.